Welcome to Math TV with Professor V. In this video, we're going to look at the strategy for testing for absolute and conditional convergence with infinite series. Now, I have an introductory video lecture on this. If you haven't watched it yet, I'll link it. Just click in the top right. Otherwise, I'm just going to do a quick recap and then draw you a little diagram if you want to use it as like your blueprint when you're testing. Okay, so what is absolute convergence? Basically, when you have an infinite series and you take the absolute value of all the terms, if that new series converges, then we say your series converges absolutely. Conditional convergence is if the original series that you have converges as is, but when you take the absolute value of the terms, then that new series does not converge. Okay. And the idea that's important to take away from this is that absolute convergence is a stronger type of convergence. So we have a theorem here that tells us that if a series converges absolutely, meaning when you take the absolute value of its terms, that new series still converges, then that means it converges. Okay, one more time I'm going to say it. Absolute convergence means that the sum of the absolute value of the terms converges. And that also means that the OG, the original series, converges. Conditional convergence is a weaker kind of convergence. That happens when the absolute value of the terms, that new series, diverges, but the original converges. And here's an analogy I gave my students. It's not perfect, but it kind of helps. You have two questions to answer when you're asked to test for absolute or conditional convergence. The two questions are as follows. Does the sum of an converge absolutely? You have to answer that question. And you have to answer, does the sum of an converge conditionally? Both need to be addressed, okay? And you can think of it like, does the sum converge absolutely, as if you're maybe on the acceptance committee at a university for a U.S. school, because I don't know how GPAs work in other countries, and you're being asked to answer the question, does the student have a 4.0 GPA? Which, if you're in the U.S., when you get an A in a class, it's assigned a 4.0, a B is a 3.0, etc. So 4.0 GPA means every single class you've gotten an A in. That's a stronger condition. Think of that question as akin to, does the series converge absolutely? And then, does the series converge conditionally? Think of that like, does the student have an A in math? Just math, just one class. And here's why this will be helpful. If you know that a series converges absolutely, then if you can answer yes to this, then you're done. You can already answer yes to this. It does not need further addressing. Just like if you can determine that a student has a 4.0 GPA, then you know for sure they have an A in math. You don't want to check the other way around. You don't want to check this first, because if a series converges conditionally, well, that's all fine and dandy, but you still don't know if it's converged absolutely, if it converges absolutely. So you don't want to check this first. You always want to check this guy first, because then that will let you know what's going on here more often than not. Just like, think about it this way. If you check if someone has an A in their math class, that doesn't tell you whether or not they have a 4.0 GPA. But if you answer this question first and you can say yes, then you know for sure they have an A in math. Okay? So let me draw you like a little flow chart, okay? My students liked the flow chart so that they can strategize. And if the question just says test whether the series converges or diverges, you don't have to do all this. It's only if the directions specify that you're testing for absolute convergence. So we always test for absolute convergence first, okay? So test for absolute convergence. Now, what test would you use? Whatever's appropriate, okay? So there isn't one set test that you use for absolute convergence. So you test for that first. Think of it like you're going to answer the question, does the student have a 4.0. Okay. If the answer is yes, the series converges absolutely, then you are done. Okay. Boom. If the answer is no, and it fails, then what do you do? Then you want to know, does it converge conditionally? That's akin to asking, does the student at least have an A in math? So basically, we know they don't have a 4.0, but do they have an A in math at least? Is there some hope for them? So what test do you use to test for conditional convergence? Always AST. So you use alternating series test to check for conditional convergence. Now, if it passes, if yes, then you're finally done and you can say that the series converges conditionally. Okay, so yes, you're done. Then you can say sum of AN converges conditionally. If no, depending how picky your teacher is, I'm a picky teacher, then I need you to show that the sum of AN diverges and you use the test for divergence. Okay. And that would be the conclusion. If you're done at the very first step, then that means the sum of AN converges absolutely. Okay. There is one more branch, okay, which I didn't mention originally. And that is when you're testing for absolute convergence, if you get a no using the ratio or root test, then you're done. That means the sum of AN diverges. Okay, so the interesting thing about the ratio and root tests is they always test for absolute convergence. So if a series fails, okay, it diverges with ratio or root test, you don't have to test for conditional convergence. There's no chance. They're kind of like an all or nothing deal. All right, let me zoom out. Maybe you want to take a screenshot of this flow chart. Yes? Do you like it? Okay. So just repeat the process, explain it to a friend. That way you have the logical steps in your head. I'm just going to jump right in. And the one exception to following this flow chart, when you get pretty good at looking at series right off the bat, if you can tell that the series already will fail the test for divergence because the terms don't go to zero, you can go straight here. You totally can. But a lot of the time students don't notice it, okay? But you don't have to go through this whole process if you notice this right off the bat. Go straight to it, okay? Here we go, example time. And I'm going to talk to you out loud, like everything that goes through my mind, so you can see how I work through these. All right, determine if this series converges absolutely, converges, or diverges. So I have to answer two questions. Does it converge absolutely? Does it converge conditionally? Always test for absolute convergence first. So here we go, test for absolute convergence. Whoop. So when you're testing for absolute convergence, you take the absolute value of AN. All that's going to do is get rid of that negative 1 to the n. So I have 1 over 5n to the 3/4 plus 4. Well, looking at these terms, this is reminding me of a p series. Okay, so let me let bn equal 1 over n to the 3/4. And what do I know about the sum, n equals 1 to infinity, of 1 over n to the 3/4? Well, for this p series, what is p equal to? 3/4, which is less than 1. So that means this p series diverges. So I have a feeling that the sum of the absolute value of an will diverge also. Let's see, how can I show it? What tests are appropriate? Well, some sort of comparison test. Can I do direct comparison? So can I show that the absolute value of an is greater than or equal to bn? Can I show that 1 over 5n to the 3/4 plus 4 is greater than or equal to 1 over n to the 3/4? No, I can't do it. In fact, it's smaller. It's a wee bit smaller because we have an extra constant here and here. So that means direct comparison is not appropriate. It's not appropriate. So what we're going to do instead is limit comparison test. So when you cannot show the inequality that's necessary for direct comparison, right? It's a very particular direction. Then we say, all right, that's fine. We'll use limit comparison test instead. So use limit comparison test because direct comparison will not apply. So we're going to consider the limit as n approaches infinity, absolute value of an, so that's 1 over 5n to the 3/4 plus 4 over bn, which is 1 over n to the 3/4. And then if I'm dividing by 1 over n to the 3/4, that's the same as multiplying by n to the 3/4. So this is limit, n goes to infinity. Now I have n to the 3/4 in the top over 5n to the 3/4 plus 4. Now to evaluate this limit, I'm going to divide by the highest power of n in the denominator. That's always the rule. So divide by n to the 3/4, top and bottom. And then we should be able to take this limit, no problem. So limit n goes to infinity, numerator is going to be 1 over 5 plus 4 over n to the 3/4. Okay, so as n gets very, very big, this term will go to 0. And so this limit ends up being 1/5. What do I care about 1/5 from the limit comparison test? All I care is that we have a non-zero constant. So this is greater than 0 and finite, which means the limit comparison test tells me the sum of these terms does exactly the same thing as whatever I compared it to. Well, this p-series diverges. So that tells me that the sum, n equals 1 to infinity, of the absolute value of an, which was 1 over 5n to the 3/4 plus 4, this diverges also. Which means, since that was the absolute value of the original terms, then the OG, negative 1 to the n, over 5n to the 3/4 plus 4, does not converge absolutely. Okay, so I took the absolute value of the terms. I figured out that that new series diverges. So that means the original series does not converge absolutely. So basically, we checked, and the student applying to our university does not have a 4.0 GPA. Is it game over though? No, because now I want to check, does that student at least have an A in math? So now I want to check or test for conditional convergence. When you're checking for conditional convergence, you will always use AST. Okay, my students love it when I say always. So here's a big deal, guys. We're going to use AST. Okay, so for AST, we call Bn the absolute value of the terms. Bn is the same as absolute value of An. So it's going to be 1 over 5n to the 3/4 plus 4. And there's two conditions for AST. One is that you show Bn is decreasing. I only use a derivative when absolutely necessary. We can show Bn plus 1 is less than Bn. Yeah, for sure. So 1 over 5 times n plus 1 to the 3/4 plus 4. I just made the denominator a wee bit bigger. So obviously that's going to be less than or equal to 1 over 5n to the 3/4 plus 4, which is bn. So that's the definition of decreasing. And the second thing I need to check is that the limit as n goes to infinity of bn is 0. And that's pretty obvious. Denominator is getting very, very large. This is going to infinity, so this whole thing goes to 0. So both conditions of AST are satisfied. So what does that mean? That means the sum, n equals 1 to infinity, negative 1 to the n, 1 over 5n to the 3/4 plus 4 converges, right, by AST, which means that the original, I'm just going to rewrite it. This is like the most thorough answer. 1 over 5n to the 3/4 plus 4. We can answer the question that it converges now conditionally. So yes, they had an A in math. Okay? Good. How was that? So let's look at another example, different scenarios, okay? Determine if the series converges absolutely, converges, or diverges. So again, I'm going to look at the absolute value of the terms first. So let's test for absolute convergence. So what is the absolute value of an? Absolute value of an is absolute value of negative 6 to the negative n. Don't get freaked out. This is the same as just having negative, let me write it as 1 over negative 6, like this, to the n, right? Because the exponent's negative. And then if you take the absolute value, then that's just 1 over 6 to the n. Well, what can we say about the sum? N equals 1 to infinity about 1 over 6 to the n. Well, it's geometric, isn't it? R is 1/6, which is less than 1, which means it converges. So if I just showed that the absolute value of the original series converges, then that means that negative 6 to the negative n, the sum, n equals 1 to infinity of that, converges absolutely. And I'm done. Why am I done? Because this is basically, think of it, equivalent to saying the student, the applicant, has a 4.0 GPA. So do I need to check that they have an A in math? No, we're good. I know they have a 4.0. They have A's in everything. I just tested for a stronger kind of convergence and it passed. So you don't say also it converges conditionally. When you say it converges absolutely, that implies, of course, it converges conditionally. Just like when you say the student has a 4.0, you don't say that means they have an A in math, they have an A in Spanish, they have an A in history. No, that's redundant. We know it. We got it. So this is all you need to say. Okay? Fabulous. See? Quick and easy. Determine if the series converges absolutely, converges, or diverges. So this one I wanted to do to show you when you get a little more experience, you don't have to necessarily go through all the steps. If I look at the absolute value of an, that negative 1 to the n goes away, so I just have natural log of 9n plus 2 over 8n plus 1. And I'm noticing something interesting. These terms don't go to 0 as n goes to infinity, right? Notice the limit as n goes to infinity of natural log of 9n plus 2 over 8n plus 1. How would you take that limit? Okay, as n goes to infinity, n is getting very, very large. Domain of natural log is all real numbers greater than 0, right? So I can pass that limit through the natural log. And we have limit n goes to infinity, 9n plus 2 over 8n plus 1. And we can just divide top and bottom by highest power of n in the denominator, which is n to the first, like this. And then just keep the ln outside, okay? You can always do this in your head too, honestly. Limit n goes to infinity. This is going to be 9 plus 2 over n over 8 plus 1 over n, okay? And then I can see 2 over n is going to go to 0, 1 over n is going to go to 0, and this ends up being natural log of 9 over 8. Ooh, and that's not 0. And remember, the test for divergence tells us if the terms of our series, the terms do not approach 0, then the series diverges. So how would you summarize this? Well, this is an alternating series, okay? -1 to the n. I just took the limit of the absolute value. So a little bit more is going on. All of the odd terms, like n equals 1, 3, 5, 7, they're going to have a minus sign in front of them. So the odd terms in this series are going to approach negative ln of 9 over 8. And then the even terms, when n is 2, 4, 6, etc., they will approach positive ln of 9 over 8. What does that mean? That means that the limit as n goes to infinity of an, the original, does not exist. And obviously, therefore, it doesn't equal 0. So our series diverges. This means the sum, n equals 1 to infinity of -1 to the n, ln 9n plus 2 over 8n plus 1 diverges by the test for divergence. So notice I skipped a lot. I didn't really even test for absolute convergence. I didn't test for conditional convergence. I went straight to test for divergence because I could tell the terms weren't going to 0 and it was going to diverge. So I just didn't even waste my time checking the other conditions or the other possibilities, okay? If you didn't notice, then what would you have done? Well, you would take the absolute value of the terms. I don't know what test you would try to use. I would just say test for divergence. There's no point doing AST. I can tell it's going to fail AST. But if you can't tell, then you waste a little bit of time. But it builds character. Okay. I have one more. Because I did draw that extra pathway in the beginning of the video. And I wanted you to see this other option. So determine if the series converges absolutely, converges, or diverges. So here we have an alternating series, and the minute you see that there's factorials, my goodness, it's time for ratio test. Don't even think about using another test, okay? It's ratio test time. And the cool thing is, with ratio test, it automatically tests for absolute convergence. So we're going to take the limit as n goes to infinity of the absolute value of an plus 1 over an. And when you take the absolute value of the terms, this alternating portion will go away, so I'm not even going to bother writing it out, okay? So this is the limit as n approaches infinity, absolute value. An plus 1, I'm going to substitute in n plus 1 everywhere. Now this n factorial is squared. To not trip you up, I'm just going to literally write it out twice instead of using the squared notation, okay? Then we have 8 to the n plus 1 over 2, put n plus 1 in parentheses, and then there's another plus 1. Yes? Good. Divided by, I'm just going to write n factorial, 8 to the n over 2n plus 1 factorial. Okay, and I didn't bother putting -1 to the n plus 1 or -1 to the n because they're just going to go away when you take the absolute value. All right, it's cleanup time. All my n's are positive, so I'm not going to write absolute value anymore. It's not necessary. So limit n goes to infinity. We have n plus 1 factorial, n plus 1 factorial, 8 to the n plus 1 over, be careful, this becomes 2n plus 2 plus another 1. So that's 2n plus 3 factorial. Divided by, so now I'm going to multiply by the reciprocal, okay, we're going to have 2n plus 1 factorial here over n factorial 8 to the n. All right, the worst part is over. Now's my favorite, where you break everything down and you have a cancel party. So we have limit, n goes to infinity. Each of these n plus 1 factorials I'm going to write as n plus 1 times n factorial. N plus 1 times n factorial. 8 to the n plus 1 is 8 to the n times 8 to the first. And then now let's break down 2n plus 3 factorial. So 2n plus 3 factorial, that's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And then everything over here, leave alone. It's ready to be canceled out. Okay? Good. Here we go. This is my favorite part. I love just slashing everything out. Bam, you're gone. Bam, you're gone. So are you. Goodbye. Bam. Bam. 8 to the n's gone. 8 to the n's gone. Cool. What's left? We have limit. N goes to infinity. In the numerator, I have an 8. I have n plus 1 squared over, now check this out. I have 2n plus 3, and then you see this little 2n plus 2? I can factor a 2 out, and then it's just n plus 1. So I can cancel this n plus 1 with one of the ones in the top. And then this is the limit as n approaches infinity of 8 times n plus 1 over 2 2n plus 3. Okay, so this is limit, n goes to infinity, 8n plus 8 over 4n plus 6. If I divide everything by n, boom, we're almost done. This is going to be limit, n goes to infinity, 8 plus 8 over n over 4 plus 6 over n. So then these guys go to 0, this goes to 0, and what do we have for our limit? 8 over 4, which is 2. Well, what does that tell me? Remind yourself, what test did we do? We did ratio test. So I always compare the limit to 1. This is bigger than 1. So that tells me my original series, the sum n equals 1 to infinity of negative 1 to the n, what was it? N factorial squared 8 to the n over 2n plus 1 factorial. Did I remember it correctly? Let's check. Oh my God, I'm good. Okay. What does that tell me? This guy diverges. And that's it. That is it. So whenever you use ratio or root test, it will automatically tell you either the series diverges, or if this limit comes out to be smaller than 1 instead, then it converges absolutely. Game over. You do not need to test for conditional convergence. Okay? So let me go back to the little flow chart. There's 3 branches. Come back, flow chart. Where'd you go? Here we go. And so basically, I tested for absolute convergence. I got a no using the ratio test, so I'm done. The sum diverges. If I had used ratio or root test and it passed, then you would also be done. Okay, so either way, when you do ratio or root test, if you get a yes, you're done. If you get a no, you're done. The only time you still have to do AST after testing for absolute convergence is if you use a test that is not ratio or root test. Okay, hope that was helpful. I know it's a lot of information. It's one of the most confusing topics for students conceptually. Totally normal. Just the more you practice and the more I would recommend explaining it to someone else as you're studying, it will help you solidify the concepts. Give the video a thumbs up if you enjoyed it. Subscribe to my channel if you haven't already. And check out my playlist. I have full-length lecture videos for all of Calc 1, 2, 3. If you want access to some exclusive content, you can join my Patreon. I have the link here in the description box. And thanks for all your support, guys. Stay tuned. I have more videos coming your way. Bye-bye.